Ready? Second part. So I think the plan, I'll be talking a little bit about just different layers that are pretty common, really only just 2 layers in the next hour, that are useful across a whole bunch of deep learning applications. And then so tomorrow is going to be a lot of small topics, but kind of for now, these are still, these are the fundamentals, right? After today, then we can cover all sorts of little topics in deep learning, but then we can more or less walk around independently across topics as long as we know these fundamentals, right? So this is basically the end of the fundamentals for now. So the plan. So for all this talk so far in the last hour long, I've only been talking about fully connected layers, right? But then in the morning, I know you read the ImageNet paper, right? And in the ImageNet paper, they talked about convolutional neural networks, right? And then if you read kind of a few years later on that challenge, the ImageNet challenge, there was the residual network paper, which also kind of substantially improved on state of the art, right? So these are the 2 kinds of layers that I want to talk about in the next hour, which are foundational in a lot of different, especially computer vision tasks. So convolutional layers and residual layers. Yeah, so that's the plan. So reviewing, this is what fully connected layers look like, right? It's like I'm mixing together all these different kind of logistic regressions. Each of those logistic regressions is looking at all the xi, right? So that's what they mean by fully connected, right? So kind of the picture is for one of these output logistic regressions, I'm looking at all the potential input x's, right? And then since I'm doing this for every single one of those logistic regressions, I have this kind of very complicated everything connected to everything else in my my single layer, right? Now, yeah, also just, I haven't been calling it this, but each of these coordinates is called a neuron in the deep learning literature. There's some interpretation of kind of, if you find a neuron that activates when it sees certain things, then like it has learned a useful representation of what's in that image, right, or what's in that scene, right? So you can think of a neuron as like a high-level feature extractor, right? So that's, but in the end of the day, it's just a coordinate in this feature representation, right? So, and kind of we already saw this formula, right? We're doing this big matrix multiplication where I mix all my weights for each of those regressions across each of my previous layers representation, right? And then I apply a sigmoid to it. Yeah, and then maybe you add a bias if you want. And that's just review. I'm giving you this because I talked about all this derivation about deep learning without telling you that this is called a fully connected layer in the literature. But now, this just so you know the words. Now, okay. Fully connected layers are not what people usually use in modern deep learning. The reason for it, kind of if you go back to this picture, you're connecting every output node with every input node. This is a lot of parameters, right? Even when you have a ton of data, that's kind of a lot to try to fit. And then there's also kind of issues where like maybe this makes training harder, right? So kind of there are a whole bunch of reasons, but in the end, you want to come up with something that's a little bit more parsimonious. And the way that you want to encourage parsimony needs to be in some sort of plausible way, right? Like you don't want to reduce the number of parameters in a way that makes your model much less expressive, or less expressive in a way that would hurt performance. What you want is something that reduces capacity without making certain functions that are important impossible to reach, right? And for a large class of problems, that kind of reduction is to go from a fully connected layer to a convolutional layer, right? You're going to see this reduces the number of parameters a lot without sacrificing kind of the most important structure. And I think before getting into what is a convolutional layer in a neural network, it's useful to think about what is convolution, right? And what's convolution in one-dimensional, or 1D, right? So this is from a wonderful blog post by Kris, so I recommend you check it out. And this is how the story goes, right? What I'm getting to is how do I convolve two functions in one dimension, and then we'll see how it works in 2D, right? So think of this story as I take a ball from some height, and then I drop it, and it can go, in real world it's going to go to continuous, all sorts of positions, but for now I just imagine it kind of goes into k different slots, right? So, and each of these kind of slots, it has a different probability of landing there. Right, so maybe you think it drops and stays kind of directly there, that has pretty high probability, but maybe if it rolls all the way to the end of the room, that's relatively low probability, right? So I can assign probabilities to each of these positions where it's going to end up later, right? And kind of just in my drawings, something I want to try to do is I'm deliberately trying to break symmetry, right? So just for pedagogy, suppose that the ball always moves a little bit more to the right. So in the picture, the branch going to the right is a little bit thicker than the branch going to the left. And the thickness of the branches are the probabilities of having that outcome. Right? So this is just probability. I'm defining some sort of k-level categorical distribution. I have assigned probabilities to each of them. Nothing fancy here yet. OK, this is fancier, but not that much more. So what I do is I drop the ball once, and then I move to wherever it landed, I pick up the ball, and I drop it again, right? And now I keep track of where it went the second time, right? So the way I would draw this is OK, maybe this is the chance that it goes to this one to the right, and then it again can go to any of these positions, right? So this is the chance that it goes one to the right again, or maybe it went two to the left, or two to the left. Right? So you can just draw out this tree of possible outcomes. And then if you wanted to figure out the probability of starting here and kind of ending up here, you just need to figure out all the paths that go there. Right? So basically, this is a device, a diagram that lets you think about the probability of different paths. Right? So even a simple computation, if I want to go right 2 steps and then left by 1, is I go right 2 steps and left 1. I multiply the probabilities, because these are independent events, and I get the probability of that particular sequence. Right? OK. And where does convolution come up? So the way I'm going to get there is that convolution is kind of what happens when you add random variables. But you'll see that in a little bit more detail soon. So in this previous one, I'm showing all the branches. Here, I'm highlighting only those branches that end up one to the right at the end. Right, so how could I have gone to one to the right? I could have gone 2 to the left, then -1. I could have gone 1 to the right and then stayed the same. You get the picture, right? So these are all the ways that I can go 1 to the right after these 2 steps. Now I just erase all the other branches. And OK, this is the formula for convolution, right? And I want you to realize that this formula is exactly the same as this diagram, right? So what is my formula? X and Y are my dropping it the first time, Y is dropping it the second time. U is the position at the end, so this is 1 to the right in this case. So I want to figure out the probability that I end up 1 to the right. Well, first I go k to the right, and then I have to go u minus k to the left. Right? And then I can do this over any of these possible k's. Right? So I can do, if k is 0, then that means I have to go f of 0, and then I need f of 1, because I'm going 1 to the right at the end. Right? And I can do this for kind of any of these possible k's. In this case, there are only 4 of them. So this infinite sum is actually just a sum over 4 things. and it's these products, right? So it's f of 1 times f of 0, right? So it would be like, and then f of 0 times f of 1, and like these are exactly the terms in that formula, right? And the reason for my introducing the symmetry thing, right? What I want you to realize about these paths are that this set of paths is exactly what happens if you flip it around and then rotate it. Or like, you get what I mean? Like first reflect it this direction and then reflect it vertically, right? That's what this kind of lower paths look like for me to make this jump, right? And mathematically, what does that have to be, right? Mathematically, the flipping this direction, that's just turning the k into a minus k, right? When you do f of x and then you do f of minus x, that's a kind of a horizontal, or like a reflection around the x-axis, right? And then the u, what that's doing, that's translating my function, right? So what's happening is I flipped it, and then, I mean, this flipping is not really relevant for the math, right? But just nice for the diagram. And then I translated it by 1, right? So it's not exactly underlying this part, but then it's kind of 1 over, right? So that's what that formula is, right? Yeah, and I think this is a useful way for thinking about convolution, right? Because it tells you something about, if you want to calculate like convolution of two functions, just imagine flipping it and then translating it and seeing how similar they are, right? Because like, or when I mean how similar, it's like, well, look at the branch sizes, and if the branch sizes are pretty big, then that means the value of the convolution is pretty high there. If I had moved my u, if I had translated it by a lot, then in this case there would actually be no branches that match, right? In which case my convolution is going to be 0, right? Because the product of all these probabilities, there's no way to get there. So my convolution is 0. And then you can imagine like all sorts of other kinds of functions kind of playing around with what is the configuration which is going to maximize the convolution. Like, well, if they're exactly underlying each other, so that like the branches have a lot of weight when you multiply them, then that's going to have a high value of the convolution. Right? Okay. This is just, when you see the convolution operator, don't look at it as this mysterious multiplication and summation thing. Just think of it as, drawing these branches and then aligning things. Okay, and then so far I've been thinking about, you drop it and then you drop it again from the same height, it's the same function, but there's nothing about my derivation that required it be the same function, right? I could have dropped it from a very high position first, looked at where it landed, and then drop it from a very low position the second time around, right? So kind of geometrically, what that would look like is my first f function could have gone to all of these possible places, and then the second one maybe only moves a little bit from that first place, because the second time around I drop it from a very small place, right? This is, if you're already familiar with CNNs, then this is already looking like a convolutional neural network, right? Because I'm translating all these smaller filters across a very big function, but we'll get there. But the point is, convolution doesn't have to be just a function with itself. You can do f star g, which is some other function. But then the exact same logic, like draw the branches, align things, and sum up the probabilities of the multiplication, that's the same. Right? So any questions? This is just convolution in 1D. It's basically how you think about summing up two random variables. Yeah. So like if you're summing up more than this, you just think of it as, I have many, many layers in my tree. So I keep on branching, and I'm branching more and more times. So yeah, there's a lot of neat math there. But okay, so in computer vision, right? So people are often using these things for convolution, or called convolutional neural networks. This is a diagram for one of, I don't have the reference. This is one of Jan LeCun's reviews on like deep learning for computer vision. And the first figure in it is this kind of canonical computer vision deep architecture picture. And the picture is always, you have a convolution layer and then a subsampling layer, which I'll talk about. And then just alternating these convolutions and subsampling, and you're building up these feature maps, right? The feature maps are basically the learned representation, like what I was calling these long vectors. You can just reshape them into images or like little rectangles, and that's what these feature maps are. And from a high level, why has this been successful, right? So kind of the first intuition I already mentioned, this is a lot fewer parameters, right? This is going to be easier to train. This is going to be kind of not as over-parameterized as a fully connected network. A second reason for them being successful in practice is that these kind of operations can be computed very fast in GPUs, actually in general. So what I'm showing, it looks like product over all these pairs. So you would think it's a quadratic operation, but it's not. It's actually n log n, and that's deep. So that's like the fast Fourier transform, right? But then, yeah, like through these sort of tricks, you can do convolution very, very fast, and it's much faster than doing a matrix times vector product, which is what you need for a fully connected layer, right? Or a fully, yeah. So that's like a second important reason why this is pretty successful. And then the last is that there's some evidence that what kind of brains are doing is like a convolution kind of in computer vision sense, right? So there's a famous experiment called the Hubel and Wiesel experiment. I don't know if you've heard of this. This is the one where like they show a cat. They've like connected certain of its neurons to some monitor, and then they show the cat edges going in different orientations, and then they show that when the edge is going in one orientation, a particular neuron always fires. But then if you rotate it slightly, that neuron turns off and a different one fires. Right? So there's this idea that in the brain, there are neurons whose job is to be sensitive to different orientations of edges. Right? And an edge detector of a particular orientation is exactly the sort of thing that you would learn in a convolutional filter. Right? So there's already some intuition that maybe trying to mix all these logistic regressions is overkill. Maybe all we need to really be able to parameterize is this sort of convolution operator. Right? So this is kind of the biological plausibility. Okay. And then thinking about image convolutions, as opposed to just, we were doing everything in these 1D sequences, right? So what, like how do I think about an image? I think of it as actually just a function on a grid, right? So if I saw like a picture of mountains, and maybe this one is a little bit darker than the first one, I just raise the value of that whole part of the image larger than the rest of the previous part. And now it's just, okay, this is just some function on a plane, right? And I didn't draw this, but then you can imagine like the tree diagram or like the ball dropping diagram in the exact same setting, like in this setting, right? Where now I drop the ball and it has this probability of landing on any of these grid points, and like a somewhat lower probability of landing on any of those grid points. So it's just the same kind of convolution, the function that I'm doing the convolution over, except it's in 2D instead of 1D, right? Okay, and then that's basically it, right? Like, I had this idea of the 2D functions on a grid, and I now am going to convolve it with these smaller functions, which are like these are functions, instead of like these 4, it would be like a patch on that image. And then I'm going to convolve them in the sense of like looking at the heights of these functions along the paths and then summing up the multiplication, right? So it's basically everything from the previous story, except on 2D, like an image function, and I take the patch is like a small it can be a predefined function or a learned function. In traditional computer vision, it was a predefined function. In deep learning, it's a learned function. And kind of the canonical predefined functions. So there's a nice example. This is all interactive, if you go to this link later. And kind of what they do. So again, this is like functional point of view. Here is, you can move around this little patch, and it computes the convolution. It just some number. So like what I do is, for this cell, I convolve it with everywhere around it. And what the convolution is, it's this summation over the branch probabilities, right? So these are different branch probabilities being multiplied by each other. I sum them all up, so that's why these are all being added. I get some number. That number I plug into that position on the secondary image, right? And this is, so right now I'm using a predefined sharpening kernel, right? So what is a sharpening kernel? This is some filter where my function has like a 5, so a very high value at the center of my patch, and zeros on the corners, -1s along the edge. So it's like I define ahead of time one of these kind of filter functions, and I just apply it across the whole image, right? Some other canonical filters, like a blurring filter, right? So if I create like a little plateau and I sum up everything within my patch, it's basically averaging everything across the patches. So when you average everything across the patch, it just kind of smears out the function value. So it gets a little bit blurred. Yeah. It also, you can interpret it as like adding noise, right? Because like adding random variables is convolution, so like adding a blurring is kind of like adding Gaussian noise, say. Another kind of canonical filter, so this is a filter with like a 1 and a -1, so it's like looking for changes like this. And then this is able to detect edges, right? Because whenever you have a drop in the function values, that's going to look like, that's going to have kind of a high product in these branchings, right? So then this pulls out all the edges in the image. Okay, you can't really see it here. But then they're like, there were like really big changes in the tree from the dark to the light. And those big changes from dark to light are being highlighted by this edge filter. Okay. Oh no, I lost this picture. But the point is, yeah, this is, oh no, I think I already had this slide. Skip that slide. Okay, and then the last for the computer vision in the LeCun's diagram, right? He alternates convolution with max or with some sort of subsampling, and kind of the most common subsampling that people would use is called max pooling. So this is even easier. This is like much easier to understand than convolution, right? All that max pooling does is I take some large image, I define a grid, like kind of even patches across my image. I take the largest value within that small patch, and I populate my new grid element with the value in that patch, or the largest value from that patch. Right? So here, the largest value here is 8 in this green piece, so I put in an 8 in the green piece. And the idea is that this takes a large feature map, it reduces it down to a smaller one. I don't have any like great intuition for why this is something you would want to do, besides that this, again, saves you a lot of parameters, right? So you imagine, well, there's the saving a lot of parameters, and there's also like some insensitivity to local translation, right? So if I translated everything by 1 or 2, then the largest value in that kind of 3x3 patch, say, would be the same, right? So it builds in that. But then I think the main point is like I go from these large feature maps, which need like a lot of filters, more complicated to train, to something that's much smaller feature maps, which are more manageable downstream. Okay, so this is the most common kind of convolution, right? This is vanilla computer vision convolution. There's almost like a cottage industry coming up with different kinds of convolutions, which are useful in different kind of settings. So I think, yeah, I mainly include it for the links. I think the ones that I know the most, so the first two are interesting because they let you do things with natural language. Right? So far I've been talking about images. You can imagine a similar kinds of thing, like here they have a sentence, right? And then they're kind of pooling information from neighboring words by like learning embeddings and then combining them, right? So it's kind of analogous to what we're doing with images, but to get the details right is a little bit tricky. And then those kind of ideas come up in the dynamic convolutions and the causal convolutions papers. Like how do you do convolution effectively on sequences? And then H-Wisp convolution and deconvolution, these are very useful in kind of like computer vision tasks that aren't just classification. So in classification, you have this big network, and in the end, you reduce it down to these k-logits, and you make a prediction on one class. But in a lot of image computer vision tasks, you want a response that's very high dimensional. Right? So like a canonical example, like they'll have these, the task is called semantic segmentation. And what they do is you can take an image and you try to figure out like a mask for where is the car in my image, right? And then I'm going to try to shade in every single pixel that is on the car, right? So for that kind of task, the output is a large image where the value in that pixel is the label for that pixel, right? So in those sort of tasks, you need to have large feature maps all the way through, right? So this sort of architecture falls apart in that setting because here the feature maps are getting smaller and smaller every step, that by the time you get to the end, it's going to be tricky to kind of get a large image again, right, in your prediction step. So in those sort of situations, the things that you need to do, either you do H-risk convolution, which is this idea of, it's basically have a larger convolution map. So yeah, they have a picture here. It's like what you have a larger convolution like receptive range, but then you just zero out some of the weights in between. So like you don't try to learn all the weights in that large field. And then the idea is this is not reducing not reducing the receptive field very much, but then not requiring as many parameters as a naive convolution with that large receptive field. It's basically letting you do large patches without having to learn all the parameters for that patch. So that's the H-risk convolution idea. And deconvolution is basically, I take one pixel, and then I turn it into 4 pixels, say. So like the most naive way is just copy that same original pixel 4 times. I just kind of upsample my image. But you can do it in a smarter way, right? Because averaging is a kind of convolution. You can think of this as like the reverse of averaging, this upsampling operation. You can do the reverse of convolution, where like I start from this one pixel, and then I might convert it into a slanted thing over that patch that's centered at the original pixel value, and that's a kind of deconvolution operation, right? So this is a way like you can learn the deconvolution operations in the same way that you can learn the convolution operations, right? And this is a way of going from small feature patches to larger feature patches, and whenever you get since you get to larger feature patches, that makes it easier to do computer vision tasks across whole images. So I'm mainly including it as a reference so that you know in the literature, these are kind of, whenever you run into large image computer vision tasks, you'll see these words. These are references for those convolution types. But there are many, many kinds. And again, it all works because you can design a new convolution layer, and as long as you know the derivative of the output of that layer with respect to the input of that layer, you can plug it in anywhere in your graph. Okay, and then last, I want to talk about residual networks. So this is kind of the dilemma that literature tries to face. On the one hand, it is, at least up to this point, they had documented the deeper and deeper you got, kind of the more meaningful the features seemed to be, and the better your performance was when you got it to work. But then it was much harder to get it to work. Either it was much more training, it was much more sensitive to hyperparameters. It was one of these things that people imagined should be possible, but it was really hard to get to work in practice, right? So that's the dilemma. And kind of like abstracting that away, what is the problem? Kind of the insight that the people who came up with the residual network paper had is that, let's say like the purple is your current guess, and you're trying to approximate black, right? One thing you can try to do is learn some like a full function-to-function mapping. But this is complicated, right? Like it's hard to get it exactly right that this is going to decrease, this has to increase a little bit. Like it's possible using kind of a series of deep learning layers, but it's a little bit trickier, right? Compared to, let's just try to model the difference between the functions, right? So the idea is I look at the difference between these two, I plot that out as some new function. And the idea is that this new function to learn might be simpler than the kind of full function-to-function transformation. And this is especially true when, let's say the two functions were actually equal to each other at a large part of the range, then this new function is mostly 0 for a lot of places. And whenever it's mostly 0, that's going to be easy to learn, right? Because you don't need as many weight updates to tell it that it's 0. You don't need any weight updates if it's exactly 0, right? Versus if I'm trying to copy one function to another function, even if they're exactly identical to each other, that's going to require weight updates, right? Because I need to learn a new layer which is exactly copying that previous layer, right? So it's easier to learn modifications in a sequential way than learning to kind of recreate the previous function from scratch each time. So that's kind of the essential intuition. Now, the trouble is, how do you encode this mathematically? It's actually not that complicated, but there's some subtleties. Okay, the first thing. Here's an attempt. I'm trying to go from the k-minus first representation to the kth representation. What might I try to do? I mean, the first thing you do, this is a slightly more general but the usual, you just do w times h, but maybe you can do other kind of operations on w and h. But you have some function of w and h. But then instead of just doing this, which is what usual deep learning would do, you add in the previous thing, right? So now this is concretely this idea that I only need to learn the difference between my two functions, right? I only need to learn the difference between the two representations. And this is much more straightforward than directly transforming the original function to the new function. Right? So this doesn't immediately work, though. So this is a little bit subtle. Is it clear to anyone right now, actually, why this might not work, or why you might want to do something different? Basically, this thing is like this diagram without this intermediate, or without this final mixing operation. And now that I want to add in this extra mixing operation, I just add in that final, that next weight layer. And then since I'm adding kind of this, whatever weights are learned by x, I can have this kind of skip. Right? So this is the diagram from their paper. Okay, and why is this useful? Kind of the main advantage is what used to be very finicky to train can be done much more straightforwardly, right? Somehow, and this is still a little bit mysterious to me, but maybe I'm sure there's people working on theoretically why this might be better. But the idea is the operations you need to do gradient descent on these kind of residual updates, it's much more straightforward than the updates you would need to do these kind of full function transformations. So you can train much deeper networks, and these deeper networks do much better in competitions or in practice. So this is kind of the diagram that they showed. You have this kind of original implementation of one of these ImageNet competition datasets, or ImageNet competition problems. You don't have as many layers in that ImageNet competition winning solution. They just tried, okay, let's just make it really, really deep and see what happens. It's almost it's like the joke about deep learning. It's what is the key to your success? Well, if you just make it more and more deep, that should work, right? And no, this does very badly. It actually is impossible to train. But then if they add in that kind of module that they had defined in the previous part based on their kind of analysis of the residuals, then it becomes trainable, and then it beats the previous by a bit, actually. Yeah, and I think that's the main parts. I especially wanted to cover convolution because in kind of tomorrow we'll talk about it a little bit, and I know some of the more applied lecturers are going to be talking about convolutional networks a lot. And I wanted to mention residual layers because kind of most modern, most modern deep learning applications are using residual layers at a lot of places, and just know it's not that much different from the original kind of deep learning framework, just it's learning these differences, so I think it's worth mentioning. I didn't really get a chance to talk about these other kind of layers, but these are very important, especially if you're doing something sequential, right? Attention, LSTM cells, gated recurrent units, so these are going to be whenever you're working with like text or language data. These are useful. And feature-wise modulation, this is an idea for if you want to work in settings where you want to introduce some sort of external conditional information, you can use feature-wise modulation. But this is more just so that you know that they're out there, other kinds of layers that not as common, but then in particular settings can be very useful.
Thank you. So just want to say that I'll be covering LSTMs, GRUs, and attention, some of the attention when I do NLP. That's coming towards the end.
Okay, I have one more. Okay. Okay. So we have 15 minutes left, and I think that's actually enough time. This is actually really only like maybe a 10-minute talk, and it's not technical, so you don't have to think too hard anymore. And this is kind of an area that's very interesting to me these days. And I mean, it's the main thing I work on at Mila. And since you've already been talking a little bit about AI in society, I wanted to share some ideas that I've found which I think are very useful for thinking about AI in society, right? And it's also a little bit of a teaser for tomorrow. Like, I know the schedule said advanced deep learning, but really the topics that I'm interested in covering are those which are somehow related to humanitarian AI. And I'll make that connection a little bit clearer in a sec. But this is the basic question, right? How do we make sure that AI benefits everyone, right? Kind of for all the attention that this field receives, it's really only being used in a very limited context, right? Like, think about all the different kinds of papers that are being submitted to these big deep learning or machine learning conferences. A lot of the applications at the end of the day, it's like you can do image classification well, you do segmentation well, you can do translation, you can do recommendations. And these are, pretty limited class of problems. And I think part of the reason it's limited is that the people who are kind of thinking, who are like coming up with the research agendas, they're not thinking as creatively as they could if they had more diverse experiences. Right? So I think we need to make sure we think a little bit more broadly about AI. And then, okay, these are some of the concepts that I find useful for, like, this is a nice dream, right? But how do you actually do something like this, right? So this is the practical, right? Two concepts I think are very useful. One is augmentation, the other is amplification. So for augmentation, there's this idea that, the thing that makes AI so useful in reality is that it actually enhances kind of existing human abilities, right? Like, even though there's all this hype about, computers that can learn to reason on their own and, fully automating everything, in reality, most AI systems are being used to just make my life a little bit easier. Right, like think about a movie recommendation system. It's just telling you something like you were going to do, or Google Translate, right? It's helping you make a communication exchange, but it's not like an independent reasoning agent. It's just giving you an ability that you didn't really previously have, right? So it's augmenting your ability. So two essays that I think are pretty interesting. One is Vannevar Bush, As We May Think. This is a really old essay. But it was inspirational for a lot of the people who came up with computers, kind of early 50s, 60s, right? If you think about it, computers are doing this kind of amazing augmentation, right? His essay, it almost kind of makes this argument that, I don't know if you know the Whorf hypothesis. It's like the idea that if you have certain kind of words in your language, then that affects the way you think. Right? So like if you didn't have a word for red, then you'd have no way of even like experiencing red. It's kind of like an extreme version of that hypothesis, right? But then in this context, it's this: if you have a computer that made certain kind of operations possible, then that changes the way you reason about the world, right? And maybe it can change the way that you reason in a way that lets you reason more effectively. Right? So that's the extreme version of this as we may think essay. And then kind of Michael Jordan, the statistician, had some very interesting thoughts on this kind of, the AI revolution hasn't started, right? It's kind of, augmentation is going to be everywhere, and that's really what we should be focusing on, rather than just thinking about autonomous kind of neuroscience agents, right? This is one class of, like one approach to AI that I think is useful when you think about kind of any sort of social application. Because in the social applications, you're not going to have an autonomous agent that solves social problems. Instead, you're going to try to find people who are solving problems, and you're going to augment their abilities. You're going to give them tools that help them reason more clearly about the world around them, right? And kind of this relates to the second concept, and this is called amplification. So most of what I've learned from this comes from this one researcher called Kentaro Toyama, who he worked at Microsoft Research India maybe 10 years ago, not in machine learning, but in a field called ICT, so Internet Communication Technology. And kind of the main point of that is that like good technology can amplify people's abilities or people's intent, but it doesn't change, or like especially intent, it doesn't change intent, right? So if you give an amazing technology to someone who doesn't intend to use it for any good reason or good purpose, then it has no, like the technology itself doesn't have that kind of moral sense, right? So it amplifies people who are doing good work, it can help them do it better. But there's also people who are doing things poorly, it's not going to have any effect, right? So yeah, it's just remember that there's a human element to all these kind of AI systems that we forget when we're just writing down the math and we're just writing down the optimization. But whenever these things are in the real world, they have that context, and that's crucial. Okay, so just, again, I recommend read history, right? There are a lot of people who have done projects like this, which aren't coming from machine learning. But then whenever you have this kind of technology in a social setting kind of problem, you encounter the same themes over and over, right? Like augmentation and amplification are two of the ones that I put out that aren't even related to machine learning per se, but which I think are, anytime you are trying to use AI in kind of a broader context, they are like lessons that we can learn from other communities. And then I'll share these slides. These are just links to all these different AI for social good, data for social good efforts that at the moment they seem almost disjoint, like lots of people are trying to do the same thing without communicating with each other. But then if we have some sense of like, this field is so broad, can we narrow down the main themes and try to actually make progress on them? I think that's going to be much more useful than everyone discovering independently of each other the same ideas. Okay, and then kind of another like high-level breakdown of what I think machine learning is useful for in this particular context. And I think this actually applies more generally, right? But machine learning, where it really shines, is in sensing and in acting, right? So what do I mean by sensing? So sensing is, there's all this information about the world around us, and we need some way of just observing everything, right? We need some way of reducing all this complexity to something that we can comprehend, right? So that's this first problem. Can we build systems that help us sense things better, right? And then the second is acting, right? It's one thing to know what's around you, and it's another to have some sort of sense of what you should do, right? They're complementary in a lot of ways. Like to have a good acting system, you might need to first have a very good sensing system. But it's still useful, I think, to have this kind of breakdown. One is much more interventional than the other, is kind of the distinction I would draw. And now I just want to give some examples of kind of in humanitarian AI situations that I've seen in the past that were successful. Like, how did they do this breakdown between sensing and acting, and kind of how did they respect these kind of laws of amplification and augmentation? So first, I wanted to include this slide after my drive from the airport. So, this is a sensing application of traffic in Jakarta. So it was done by UN Global Pulse and Data Science for Social Good. What they did is they have cameras at intersections in the city. I think it's maybe like 20 cameras. It's not that many right now. But they got video streams from all these cameras. And then they were basically tasked with, okay, can you kind of, one, figure out the least safe intersections? Two, figure out where we should put our kind of traffic, like a director kind of people. And then kind of three, if we were going to build any kind of larger infrastructure project, where should we build things, right? So that's the high-level question, and you need to figure out what are we going to do. So this is like the augmentation side of it, right? Like there is no automated machine learning designing how to build roads. Like that's not ever going to happen. But then we can build systems that process all this video data and help guide people, right, towards this is like these are the dangerous intersections, for example, right? So how do you do it? What they propose is first you do some sort of object detection. It's like a canonical computer vision task. And then they do something called optical flow estimation. So the optical flow is telling you that these cars are moving in this direction, this car is moving in this other direction. From just this information, they're able to find like cars moving in the wrong side of the road. They're able to find cars that are stopped in traffic. And they basically, from these rules, they come up with a list of kind of problematic traffic behavior and are able to go through many, many more hours of computer like traffic video than you'd ever be able to do by hand, right? So this is the sensing element, right? It's taking this huge amount of information and compressing it to something very simple. And actually something that can inform your decision making, right? And then I think the last point to keep in mind is like, in terms of augmentation, right, it's helping guide people's decisions, like amplification, right? If you trust the Jakarta traffic infrastructure people, this is an amazing tool, right? This could potentially change the way that they do their work. But if you don't trust the traffic people, then maybe they're just going to use this to like more optimally give tickets to people who need tickets, right? Like that is not what you want. Like that is like the opposite. That's like negative amplification, right? So again, like these solutions never live in a vacuum. They only ever kind of amplify human intent. That's the first one. Kind of a second application that I think is kind of cool. So the problem is you want to have kind of land cover maps for kind of large parts of the environment, right? So, I mean, you can't quite see this, but there's like an aerial image, some plane flying over. This is in the US. But it just collects tons of these images. For some of the places, you can label it in high resolution, right? So you just say, this is a road, this is a forest, this is a field, this is water. And you can build all these kinds of maps, but that's very, very time intensive to do these labels, right? This is much harder than say like, oh, there's a cat in this image, there's a dog in this image, right? This is, you have to go pixel by pixel and like say this is what the class is. So it's extremely expensive. But then they're able to learn mappings from a few labeled examples to get all these other kind of land cover maps. And kind of what's amazing about this is there are a lot of downstream tasks that depend on these land cover maps, right? Like the most kind of critical ones are kind of ecological, right? So they worked with an agency called the Chesapeake Conservation Agency, and they're able to see things like deforestation happening. They're able to see like rising sea levels. So it gives you a very accurate, high-resolution, like mathematical description of kind of these broader ecological problems, right? So this is helping you sense the world more effectively. Okay, so this isn't machine learning, really, but I think it's an area that machine learning is kind of being used more and more right as we speak, but I still think like the classical thing is great. So this is something called the Humanitarian OpenStreetMap. So the idea is whenever there is kind of a big disaster or like a hurricane, right? Emergency responders need to have access to kind of detailed descriptions of the places that they're trying to aid, right? It's just so they know, like, is there a bridge there? Like, are these highways, like, are they paved so that I know that are they wide enough so I know my relief vehicles can go through, or are they too narrow and then I should plan an alternative route? So you need to know that sort of information when you're coordinating an operation like that. And this information is not that easily accessible, right? There's something called the OpenStreetMap, where people, like crowdsource volunteers, just go in and label things, right? So that, like, people in their free time, they stand at some corner and they say, like, there is a hospital here, or like, this road is made from asphalt, this road is made from dirt, and they tag features in this map that's kind of crowdsourced. The interesting direction where machine learning is being used on this now is that you can, from the satellite images and examples from this previous OpenStreetMaps, try to learn kind of other OpenStreetMap areas, right? So the idea is, in this image, they had a concerted volunteer campaign, right? From the left was this kind of area in Brazil before they had a directed effort to map it, and on the right is after they had a whole bunch of volunteers focus their effort on mapping this city. They got a lot more roads, they got a lot more features in, right? If you can do that in a more automatic way, this is very relevant for all sorts of social action, right? And again, this is something that computers could do. Like, they could look at satellite imagery and figure out that there are roads in certain places, right? So that's the last sensing example. In terms of acting, there's this famous application. What it's doing is there's some app, it's looking at these leaves, and it's finding all these whiteflies. And the reason this exists, so the whiteflies are bad for the crops, right? The agriculture workers, like, for monitoring purposes, they used to have to count these by hand, right? Which is extremely tedious, right? But now you can just, like, put a camera over it. It draws these things. It makes a few mistakes, but that's okay because you can process way more plants. And yeah, again, this is like the Vannevar Bush idea, right? I'm enhancing the abilities of people so that they don't have to waste all their energy doing things that aren't worthwhile. And in terms of amplification, I think it also works because it's not like you're giving this to random people to count flies. You're giving it to the people who might actually be able to make downstream decisions about where to treat which kind of crops. Okay, there's another, this is, so Charles is at Mila now, and this is kind of one of his big projects. So the problem is there's a certain kind of birth asphyxia, which is very problematic, where it can lead to kind of severe cognitive difficulties if it's not treated. And it's kind of hard to tell, actually, like, especially if you're not a trained doctor, you don't know the difference between, like, a normal cry and a cry because a baby has asphyxia, right? And he's come up with an app that will help in this preliminary screening stage to say, like, oh, maybe this baby needs to be examined by a doctor, right? So now people who kind of might have ignored it or might not have had any way of knowing whether or not this is a problem have some kind of easy assessment, right? And I think of this as, like, action because it's telling you more directly, like, you have some choices of decisions to make. It's not a matter of just knowing everything in the world. You need to make concrete, options here. So, yeah, this is, I think, a canonical example there. And then another project. So this is in Chicago, actually. This is, to the best of my knowledge, it's the first time a machine learning algorithm has been legislated into law. So it's now part of the City of Chicago civic code that lead inspections will be done according to, I think it's like random forests or something like this, right? Maybe like one day, if there's ever like a political campaign with like, no random forest, we need deep learning, that will be like, we've made it as a society. But yeah, unfortunately, the debates are not nearly as interesting. Okay, but the point of this study was you want to inspect homes for lead paint. because lead paint can have, it can be toxic for babies. It can cause issues for children who eat the paint, right? Ideally, you would be able to look at every single home and say, like, okay, this one lead paint, this one doesn't have lead paint. But there are not nearly enough inspectors to actually do that. So what this turns into is a resource allocation problem. And a lot of problems actually have this flavor, where it's, you have a fixed number of inspectors, you need to allocate resources across a certain number of them, do this in the most optimal way. And kind of they're able to say, like the figure, what it's basically saying is that when you change your allocation of the inspectors in a way that's driven by historical data, you can reduce the actual number of lead. Basically, like the inspectors are inspecting homes which actually have lead and not those which don't, right? This is tricky business. Like if you all of a sudden start learning features that are saying that this neighborhood always has lead paint, always go there, and it turns out another neighborhood is starting to have problems, you need to balance the like exploration and exploitation, right? Like you need some sense that like you're not just reinforcing patterns from the past. But this is the idea, right? Like somehow learn a way to allocate resources in an optimal way. Okay, and kind of all the topics I'm going to be talking about tomorrow are linked to this, like this acting sensing duality, right? So Bayesian deep learning, the reason I think of this as being very related, especially to acting, is that it helps you inform your decisions in a probabilistic way, right? So instead of saying, you know, like, instead of saying this baby has asphyxia, this one doesn't, you give some sort of probability associated with it, right? Or you give some sense of like, not just like the probability, but like, this is the probability and I'm sure of it. Or you say like, this is the probability, but I have really no idea, right? And that sort of information is very helpful for if you're planning on ever doing a real decision in the world, right? So meta-learning, this is this topic where you have many small data sets, and you want to learn some sort of information that shares information across all the small data sets. And I think this is important. Inevitably have lots of heterogeneous, like small sample size data sets, right? You never have kind of uniform large data sets, which is what was common in kind of the internet tech company paradigm. So knowing how to manage heterogeneity is critical in these applications. GANs, this is a little bit more of a stretch. Like people use GANs for all sorts of things these days. I mainly just wanted to talk to you about it because I want to demystify it a little bit. But then I've also seen some interesting work about you know, thinking of GANs as unsupervised models or like semi-supervised models. It helps you work with fewer labels, right? Because GANs at the end, you'll see, are like ways of modeling just the distribution of features without thinking about class labels. So if you can learn how to model that well, maybe you need fewer labels. And there's also some interesting work on domain adaptation using GANs, right? So you can learn to have models that work across heterogeneous settings, again, using this. And then the last point, so interpretability, this is kind of a more popular topic these days, right? And it's especially important in humanitarian applications, right? Because, you know, again, this is related to Bayesian deep learning. When you make a decision, you want to be able to understand, like, if I had changed my data slightly, if I changed my model slightly, would I be doing things any differently, right? So, yeah, I think being able to ask these sort of questions of your model is important for any kind of real-world application. Okay, this is kind of all of what NAMI is about, and in winter school we want this sort of research to be inclusive. We want the development to have all sorts of perspectives, right? I'm hoping that through my talks I'm making it clear that, you know, even though there's all these papers and there's all this attention, in the end it's just the chain rule. It's just something you learned in high school, right? It's doable, right? And then I think like the other reason for wanting this mission, besides, you know, inclusivity in and of its own is a value, right? The other reason is if you leave it up to us Californians and Canadians to do all the deep learning work and machine learning work in the future, like I can tell you already, the things you're going to get are better movie recommendations, because that's all Californians do. And like, how do I like more efficiently find the closest coffee shop? Because in Montreal, like what else? So like, and that's really like, if you look at most deep learning applications and startups and stuff, like that's the sort of thing you see. And that's a little bit disappointing, because there's so many kind of interesting problems that people could be working on. And I think like if we have more perspectives, then we will see more of that interesting work. So yeah, this is just prelude for tomorrow.
Okay.
Your previous slide is that deconvolution just about reconstruction of convolved data or feature map, or is it about other way?
Yeah. So, okay, you can actually use deconvolution in all sorts of operations, right? So kind of before deep learning, you would use deconvolution a lot if you're trying to do some sort of super resolution, right? So you're like upsampling an image to get an enhanced version of it. But in the deep learning context, I think it's mostly used to go from kind of low-res feature map to a high-resolution feature map. I don't know people who do anything directly with deconvolution there. But it's like it's an abstract enough operation that you can use it in whatever kind of context you care about.
Okay. No.
Just a simple question: when we are talking about deep learning, when is it good time to use an end-to-end deep learning?
Kind of like if you think about cybersecurity in general, what a lot of it boils down to is like there's this problem called anomaly detection, right? So it's like most people are behaving in a certain way, but a few people are behaving in very atypical ways. And in terms of probability and in terms of data, this is like you have some distribution over points, and then the points with very, very low likelihood, these are anomalous points, right? And kind of, so there's that whole, any kind of like probabilistic description is useful for anomaly detection. And there's another dimension of the problem that makes it kind of interesting, is that you often think about behaviors as graphs, right? So like kind of people who interact with each other, like this is like the canonical kind of NSA style interaction graph of people, like who emails who calls who, right? And you can learn anomalous patterns in these networks. And for network modeling, there's a field of deep learning called graph convolutional networks. So that area ends up being useful for if you want to describe behaviors on a graph that are very atypical. Yeah.
One question regarding the max pool comment that you made. So we had this very interesting debate about max pool. Can it be replaced by stride 2? If you make stride 2, the parameters will decrease, right? So there is the interesting debate that max pool should not be replaced, saying it acts like an intuitive filter. Like it will force network to pick local features which are really important and pass them to the higher to the right side. But we couldn't justify the intuition behind that max pool filter will do that. So I wanted to know what you think with it.
So okay, this is something that some people have very strong opinions about, but which I don't really have a very strong opinion about. So like there are people who say that like H-Wis convolution, which is the kind of convolution where you have the gaps, that they prefer that over doing max pooling. I think that's the right description of it. Other people say like, well, it's worked so well for so long, why do you need to change it, right? Other people say you shouldn't ever use it for other reasons besides H-Wis convolution, right? So there are these debates. I feel like I try to disengage from these like purely architectural considerations, unless there's like you can ground it in some sort of experimental point of view. Like I dislike if you're just kind of making proposals based on like very limited evidence about this architecture must be better all the time. I'd much rather see like a careful experiment about in these particular contexts. I have a hypothesis about why this architecture might be better, and I monitor the statistics that either help me accept or reject that hypothesis.
In case of deep learning, it must take a much longer time to acquire the final solution. How can we manage the time complexity and lower the time?
Okay, so that's a deep question. There's like several directions of research that are aiming to do things like this. So just for a flavor of it, like there's obviously the pure kind of hardware computer, like a kind of architect, like a hardware design people who are thinking about like, are there particular hardware we could build, like all this tensor processing unit is kind of along that direction, which are suited for doing the kinds of operations, so that maybe you can do that faster. There are people who come at it from an optimization point of view, right? Who think like, if you can find alternatives to SGD or Adagrad or Atom or whatever, if you can find a version of the optimization that's more efficient, then that could be one solution. From the kind of architecture design point of view, there are people who say like, maybe if you can find the version of convolution for other kinds of data domains, then that kind of architecture might have fewer parameters and it might be easier to train in the same way that like convolutional networks are easier to train than fully connected things. So if you could do that for other domains, that might be one way of speeding it up. And then finally, there are the people who approach it from like a transfer learning or like meta-learning point of view, where they think, oh, if you've already trained on similar tasks, like this is like the question about the natural images statistics, right? If you've trained on natural images before, you don't need to retrain all those parameters for the lower level filters, because they're probably really similar, and it's only the high level things that you need to change, right? So if you could do transfer learning well, then maybe you just spend a lot of time training one model, and then you slightly change it for all these other models. And each of those small changes should be much easier to like it could be really fast, it could be real time.
This might be a bit personal for you, but I think it would be worth sharing at Nepal Winter School. So at which point in your academic career did you start focusing on humanitarian AI, and are there any particular problems in the society that you wish to solve, or was there anything particular that made you want to work on something like this?
Okay, that's an interesting question. Like it was much less deliberate than it might seem in hindsight. I think like the story of how I got into this topic, like the actual story is that it was the first week or two of my PhD, and then one of the new professors decided he was going to create a reading group about social good and statistics. And then I remember thinking, it's like, oh man, I have my quals at the end of the year. Should I join this? And then in the end, I decided to join it, and that changed everything, clearly. But no, yeah, that was really it. Like, I went to that reading group, and this is Professor Mackey from Stanford, and yeah, it's just like, none of us knew what we were doing really, but we just emailed a whole bunch of organizations. It was something that kind of volunteered my time with. And then later I did this data science for social good fellowship, which is what Samrachana also was. She was one of the initial fellows for that program. So I think through those two experiences and then like volunteering kind of all over the place, yeah, that's how I got into that field.
Application. So in deep learning, we are hoping that the model learns from the a lot of low-level details from the data, and then so it requires less of domain expertise. But I imagine for some applications, that's not quite feasible, and maybe for some humanitarian AI applications as well, it's crucial to integrate some of the domain expertise into the models, or into at least the whole system as a whole. So is there any work being done in integrating in ways to integrate those knowledge into deep learning models, or is the techniques that we handle, or do we fall back to more traditional methods to handle those areas?
Yeah, this is a good question. It also touches on kind of the reality that a lot of these deep learning applications aren't very scientific, right? They're kind of engineering or like technology industry focused. But for it to be really useful in science, you should be able to incorporate existing scientific knowledge, right? But there are pushes in this direction, right? And the kind of main pushes I can think of right now, kind of in the whole Bayesian deep learning community, the whole point of Bayes' rule is that you have a prior, and then you update your knowledge of the world starting from that prior. But if you can encode knowledge about the world through that prior, that's kind of one way to go. Actually, eliciting a good prior is tricky, because most of the times when I write down a prior, I define it in terms of parameters. Like for the beta distribution, right, the coin flipping stuff, you specify it in terms of the parameters of this distribution, when really it should be you should draw the function, or you should draw like the downstream consequences of that prior belief and then have people validate it. So that's a field called like prior elicitation. So there are ways of doing elicitation that are like figure out the class of priors just from like a GUI that the user can interact with. And then outside of the Bayesian deep learning point of view, there's all sorts of like structured regularization, or like a kind of architecture design, which can account for particular knowledge of your problem. So like one example comes to mind is Joshua has this paper on sparse attentive backtracking. So the idea is like you do attention, but then usual attention in kind of translation models, say, is like you have some amount of attention for all the history, for all the words in your early sentence, right? But then in sparse attention is you think that, well, really only parts of a sentence might be relevant, and you just ignore the rest of it, right? So this is like a prior on the way people pay attention to things, which is different from like what the model had been doing. And this somehow lets you work with much longer sequences, because if you're only looking at a few pieces at a time, right? So I guess the point though is like you can try to encode that existing knowledge in these sort of architectures or priors. Doing it is still a pretty involved process. I think like one of the dreams of kind of machine learning in general is like it shouldn't just be fast in terms of computation time, or it shouldn't just be accurate in terms of like statistical accuracy, right? But it should be kind of usable in like human time, right? So like I should, as a scientist, be able to write down like what I want, like what model, or like what properties of my model I want it to know about already. I should be able to specify a model and fit it all very quickly, so that I don't have to worry about my modeling and I can focus on the science, right?
How can we convince the policy makers to use machine learning-based solutions to solve different problems of the country?
Okay, yeah. This is a question of adoption, right? So I don't think there's any sure way. This is like probably someone who studies policy and someone who has more of a government background, probably much more qualified to answer this than me. My intuition, though, is that in a kind of large group of policymakers, or like consider, say, like everyone who thinks about food insecurity, say, and there's a whole bunch of people who think about food insecurity. They approach it from many different ways, right? Some of these people are going to be more competent than others, right? My general intuition is follow the people who are competent help them be more effective. And then eventually, even the people who are kind of resistant to change or who are very conservative or who don't want to experiment with things, they will see the benefit if you can show a very nice example and provide a template with one partner. And if you can show that template, then it gets much easier for people to adopt it across. Like people get like data envy. They're like, oh wait, they're doing it with data. We can do it with data too, right? And then soon everyone starts doing, right? So yeah, I think it's like, if you find someone who's not receptive, don't waste your time with them, because it's going to, like, you're going to go through a lot of effort and it might not work in the end anyways. So like find the most promising partners, and then maybe eventually the whole field will move.
You showed before in the humanitarian AI side about the different efforts going around for data science for social good.
Oh yeah.
Yes, you said like you were like all of those efforts were kind of siloed, and you're trying to organize them in specific like different themes. So I just wanted to know if you could tell us a little bit more about what you are doing there and what those themes that you are organizing them around are. Thank you.
Okay, yeah. So I should make it clear that so far my efforts have been very just like me trying to make sense of the field rather than like actually coordinating all these different people. It's more like, the way I think of it is, if you're trying to enter this area, like, it's nice to just know what all these different groups are. But in terms of like how I'm organizing it, so like there are many different dimensions that you can try organizing it, right? Like the most obvious dimension is the kind of social problem that they're trying to solve, right? So, you know, is it emergency response? Is it homelessness? Is it food security, right? Like you can divide it into that kind of grouping. Another dimension that is useful to break it down by is kind of, who is the audience for the effort, right? Is it like high-level policymakers who are trying to legislate? Is it kind of on-the-ground government workers? Is it like the beneficiaries themselves? So this is another axis that you can break down these efforts. Another is, who does the work, right? So I find like a lot of these efforts are volunteer-based. And even among the volunteer-based ones, there's a difference between people who do it as hackathons and people who do it as kind of dedicated fellows or interns, right? They're academics, they're non-academics, they're government groups, they're social enterprise, like there's all the sorts of people doing it themselves. And I think like the most interesting way to break it down, the one which I have like the least sense of how to actually do it, is like kind of, how do you find the high-level research abstractions so that like these are the canonical research problems that once solved will help across a wide range of social applications, right? I think like one example of that is this kind of resource allocation problem, right? So where you know, a lot of situations you either have like actual inspectors or some notion of like a limited resource to give out. If you can figure out like the canonical social application of that, that could be an interesting problem to solve. But then, yeah, this sort of breakdown, I don't know.
Okay, we are taking the last question. So is there any explanation aside from training difficulty?
The kind of only intuition I've heard before is that if kind of it's basically the same as like in recurrent network, or sorry, yeah, why is training just a vanilla RNN so hard, right? It's because the gradients vanish eventually. Because you're multiplying all these gradients with each other. If it's very long, you have more chance of it just getting zeroed out by the end, right? So like if you monitor the gradients in these very deep networks, you experience the same kind of phenomenon, right? Like you are updating the weights at the high level first, but then it never really propagates itself back all the way to the beginning because you multiply all these things that get to zero at the end. So that's the one intuition I've seen. But there might be other explanations that I don't know.
Okay, so I think we're going to close this question answering session. So let's thank Kris for his very interactive session. So now I would like to ask Pascal to come and present.